I'd like to do then is spend some time today looking at how do we measure air pollutants. We'll look both ambient monitoring and we'll look at source testing. Be relatively brief, not going to spend a lot of time on it, but I do think it's important for you to understand the difference between the two and the complexities of air quality measuring. So as I mentioned, there are two different types of air pollution monitoring. One is ambient monitoring and the other is source testing. So ambient monitoring is an attempt to assess the concentration of pollutants that the public breathes. So these really relate to, in air pollution lingo, the NAAQS, the National Ambient Air Quality Standards. So the primary goal of this program is to protect the health and well-being of people and also the environment. So in order to do so, we need accurate data about the ambient concentrations of these pollutants. On the other hand, source testing is related to determining the emission levels from an industrial or other source. So we're looking there at concentrations, we're looking at flow rates in order to determine the mass of material that's being released on an hourly or daily basis. Some cases an annual basis. All sampling involves essentially these components. So we have some sort of gas flow, we have an inlet device, and that is often designed to exclude unwanted materials. We have, in some cases, a device or a procedure that separates out the analyte that we're trying to measure from everything else, or may fractionate the particles, for instance, in the case of particulate matter based on size. You also may often have a sampling probe that's heated because you don't want condensation. The condensation can cause corrosion, can cause deterioration of your sampling probe, so you want to prevent that from occurring. And then there's a detector, and there's some sort of a pump or vacuum to move air through this system. And lastly, we often need a gas meter so that we can measure the flow rate. And feel free to interrupt if you have any questions. Now, let's look at ambient air sample. Monitoring of air quality is complex. It requires the collection of data that allows for a resolution of the dynamic nature of air quality in terms of both spatial and temporal variability. So we need samples that are representative. So, for example, if we were to measure carbon monoxide, where might we sample in this image here? So we're looking at carbon monoxide. Where would we sample? Any thoughts? Okay, downtown. We want to sample carbon monoxide, typically in an urban environment, close to where there's traffic. So we're going to do it, measure downtown. Given this scenario here, where might you put the carbon monoxide monitor? Got a few locations, really three, that they kind of give you in the image. Which one would you choose? Do we put it in the parking lot, in the parking structure? Do we put it on top of the courthouse? Do we put it somewhere, let's say, right above this window here? Where do we want to put the carbon monoxide monitor? By the office building. So why would we put it by the office building? Well, what we're looking at is with carbon monoxide, we're looking at what are people breathing? What's the likely exposure? So you want it close to where people are located. If we put it on the roof of the building up here, likely we'll see lower levels than what most people are exposed to because there'll be dispersion of that carbon monoxide. So that isn't representative of what people are breathing. If we put it somewhere in the parking structure, it's likely to be greater than what most people are breathing. So typically with carbon monoxide, we would want it located about 3 meters off the ground. We want it located, in this case, downtown near the source so that we can get a sample that's representative of the exposure. The other thing to think about are what are the physical needs for monitoring. We often need power. We want the monitor to be sheltered from rain or snow. We want it protected from vandalism. We could have put it lower than that 3 meters, but that puts it closer to a location where it could be vandalized. And if possible, we'd like it at a location that isn't going to charge us rent for it. We also need to think about how that sample could be altered in the process of collecting the sample. And you can kind of think about that we want to think about, or we want to prevent the sample from, or the analyte from being changed during sampling. And I mentioned this in the other sampling video. So we talk there that in some cases, for instance, samples are collected in amber bottles. And that's done when your analyte is photoreactive. So you want to make sure in that case that you're not sampling that in a clear vessel subject to light that would degrade. So chlorine, we did the chlorine residual lab. Chlorine is photoreactive. You should have seen that it degraded faster in the sunlight than it did in the dark. So you have to think of we wanted to see degradation, but if you wanted an accurate level, you want to make sure that your sampling isn't changing the analyte, either changing the analyte or changing the concentration. You want to think about how can that analyte sorb, or will that analyte sorb? So some chemicals will sorb onto plastic, some will sorb onto glass. So you want to make sure that you're protecting essentially that analyte and the integrity of that sample, both during the sampling process, but also during the collection and then transport, if you're transporting that sample back to the lab. You also want to make sure that the process that you're using meets all of the US EPA and state regulatory regulations. There are very strict regulations, both in terms of how the sampling is done, so both in terms of the sampling, how the analysis is done, how the equipment is maintained, how often quality control, quality assurance measures are taken, and then also in terms of time scale you're actually measuring. So for instance, you see here, you're looking at particulates, and this is a 24-hour averaging time. So you need to be able to average at least over that period of time. So within all of the regulations are the exact procedures, the sampling intervals that are necessary, and I'm not going to go into that kind of detail at this point, but those are prescribed by both EPA and also the state regulatory agency. With source water sampling, or source sampling, so here we're talking air, it's just as complex and just as challenging as ambient monitoring. And that's because in most stacks, the gas flow will vary both spatially and temporally. The concentration, so because of this significant change, or these changes, that makes monitoring much more complex. You can get a sense of the variability in this image here. And what is done is they've sampled both the gas velocity and emissions, and this is just on a relative level. So you can see that the gas velocities vary from about 0.2 all the way up to 1.3. And then the emissions vary from 0.1 to 1.9. So in order to actually assess this, if we were going to measure the mass emitted, we would multiply the velocity by the concentration by the surface area here. And if we do that, just to give a sense, and this is all relative to the average, but the minimum would be around 0.96, so about 1, and the maximum would be about 118. So you've got this tremendous variability spatially. And the question is, how do you take that information and then get an accurate quantification of the mass of material that's emitted? Now, if you sample further away from the bend, there isn't quite the variability that you see at the bend. So you want to be careful of where you sample. The other thing that's challenging with source water sampling is the location of where you sample is not necessarily easily accessible. And you have to be able to sample in all weather conditions, irrespective of where that device is. And you can get a sense on the image on the right. It's quite high, and typically the sampling stations are quite high on the stack. Now, EPA has attempted to standardize some of this. This is again a stack. You can see where there is a sampling station right up here, and it's designed, and they've specified, for instance, where you would sample. So there's specific locations of the ports, there's specific locations. This is on a rectangular stack, how you would sample, and then on a circular stack. So EPA attempts to provide guidance for this so that you can ensure that the samples that you gathered are, in fact, truly representative of the mass of contaminant that is leaving that stack. Again, looking at the sampling system, we have 4 different systems here. And again, just basically most, as I said at the beginning, the essential components of these are the same. So as you can see, this first one here, we have a manifold. So the manifold is transporting the material from the ambient atmosphere to the collection medium or the analytical device. And you want this away from heat, sunlight, high humidity, if at all possible. And then you have the collection medium, and this could be a solid sorbent. It could be a liquid sorbent. It could be a filter for collecting particles. It could be a chamber for collecting a volume of air. You will often have some sort of an air mover, so a vacuum or a pump, and then a flow meter. The first device here, A, is typical of many extractive sampling devices. So for instance, ammonia can be collected in a liquid sorbent. Hydrogen sulfide can also be collected the same way. PAHs, polycyclic aromatic hydrocarbons, can be collected on a solid support like activated carbon. The second here is, think of this as an open face filtration system. This is just like a filter that you would have in the lab. You've got some sort of a filter media. You're pulling air through that, and you've got a flow meter to measure your flow rate. C is a stainless steel or Tetlar bag. So stainless steel container or a Tetlar bag. You've got some sort of evacuated container. You're filling that with the air that you're looking to monitor. You would seal that and then take it back to the lab for analysis. And then D is more of a continuous monitor. SO2, ozone, NOx are often monitored using a continuous monitoring system. So you have some sort of a flow meter. You want to make sure that that flow meter doesn't alter your sample. Then you've got a detection chamber, and then you've got your pump or vacuum to pull air. So these are typically really the 4 types of systems that are used for monitoring air. When you're looking at the different air sampling systems, you need to think about the collection efficiency. Are you collecting all of the sample, or are you somehow excluding a portion of that sample? I've mentioned the potential for reactions or sorption. So you need to think about sample stability. You need to think about recovery. So for instance, I mentioned sorbing PAHs onto activated carbon. You need to be able to desorb the PAHs in order to measure them. So you need to know how much can you actually get off and extract off of that activated carbon and then measure. And as I mentioned previously, you want to make sure that there are minimal interferences or changes in the material. if your flow device is reacting with the material. So for instance, if you're measuring ozone and you have rubber gaskets, which will react with ozone, and those rubber gaskets can come in contact with the ozone, you're going to get a reaction. You're going to diminish the concentration of ozone, and your concentration is no longer representative of what was out in the air. I've mentioned extractive type samplers. So what you see here is a bubbler. So this would be filled with a liquid. You then pump your sample through it. You dissolve the analyte. So as I mentioned, this can be done with ammonia. Any soluble gas you can measure this way. So for instance, ammonia, hydrogen sulfide can be monitored this way. So what you're doing is you're measuring time and flow rate, and then you will measure the mass in this volume of liquid. You can also use a solid support. So there's a variety of solid supports. 10X is polymeric material. You can use ion exchange resins. You can use activated carbon. You have some sort of a sorbent here. The air flows through that sorbent material and is held onto that sorbent material and then extracted later for analysis. And then these are Tetlar bags. So you can collect in a vessel, it can be glass, stainless steel, or these Tetlar bags. With particulates, we often want to know the mass concentration, and size is particularly important because the smaller the particle size, the further into the respiratory system that particle will be transported. So very small particles, submicron sized particles, can be transported all the way deep into the lungs, into the alveoli, and even cross the alveolar membrane into the bloodstream. Larger particles are removed in the nasal passages. So because of that, we're often very concerned with the size of the particles. So we will often collect, and when we collect, we fractionate the particles based on size. And what you see here is what is referred to as a cascade impactor. You've got plates that here, and you've got size holes that are different size, that because of the size, the density of the particles, they will deposit on different plates, and you can fractionate the particles in this way. We also have passive sampling systems. These don't have any moving component, and they're predominantly used in an occupational environment. So for instance, if you were to work at the Frib, you would wear one of these. In fact, you would wear it at all times, wherever you were working in that building. Whether you were filing paperwork or actually back in the lab doing lab work, you would wear a radiation monitor. These are located close to the breathing zone. You would typically wear them close to your collar. You can also use these for measuring radon gas in homes. And the advantages are they're low cost, they're reliable, they're convenient, they're portable, they're lightweight, and they're specific to a particular person. So for instance, if you worked in the Frib, you would have your monitor that is your monitor alone. Nobody ever touches it. Nobody ever uses it. It is yours. Because what they have to do there is they have to monitor your annual radiation dose. And if your dose exceeds a certain level, actually on a daily basis, but also on an annual basis, then you no longer can work in that building and they have to relocate that person elsewhere. If you were working in an occupational setting where you had a potential exposure to ammonia, to benzene, you often will be required to wear this type of a monitoring device to ensure that you are protected against high exposure. We've also set up a series of stationary monitoring networks all over the US and now over much of the world. Now, the goal with these is to determine the impact of both new and existing sources of emission. So what we want to know is there a significant change in air quality? It's used for background data for instance, for an environmental impact statement. So for instance, a new natural gas-fired power plant is planned for the area. Let's say this is not. But in order to get a permit to construct, you would have to demonstrate that that facility is not going to cause significant deterioration in the air quality. So, but you need to know what the air quality is existing. So then you've got this background data. You may have to do additional analyses, additional monitoring. And then once that facility becomes operational, you're monitoring to ensure that there isn't a significant deterioration. You can also use it to determine long-term trends. You'll be able to use this type of information to determine, is there a significant increase, for instance, in PM 2.5 during holidays where fireworks are often set off? Is there a significant change over time? Are we seeing worsening air quality over time as a result of industrialization? Is it specific to particular times of the year, particular to specific holidays? So looking at these long-term trends help us to assess the impact of various different events. So these stationary monitoring networks provide us with background concentration levels. For instance, when EPA looked at the ozone levels, they needed to determine what were the background concentrations. What is a reasonable level at which to set the limit? How low can we go, essentially? So you're looking at all of this data to assess that. You're also looking at what are the maximum concentrations? Are there significant increased concentrations in certain areas? Do we need to do something to improve the air quality in that area? There's also a lot of need to look at issues of environmental justice. What is the impact, especially in higher density, lower income areas? And are they exposed to higher levels of pollutants and therefore have worse health outcomes? We look at local sources. You can also look at remote sources. It's interesting, if you looked at the data for wildfires, particulate matters, back when the wildfires were really bad out west, what you could see just from see it most at night in a sunset. The sunsets were really weird. They were strange because of the high particulate levels, but the particulate levels were actually in the upper atmosphere. If you look at the levels measured in the upper atmosphere using satellite data versus the levels measured at ground level, you'll see that the levels were actually much higher in the upper atmosphere. So thankfully, what we were exposed to at ground level was actually significantly less than what was in the upper atmosphere. And you can look at the impact of natural and anthropogenic sources. We also, how we set up the monitoring stations really depend on what information we wish to gain. So for instance, if you're looking at that personal cloud, you're going to use the personal monitoring stations, but not monitoring devices really, and you're going to measure in the breathing zone of the particular person. If you're looking at more of a neighborhood level, that's typically a 1 to really closer to 100 meter, you're looking at sampling at what we refer to as a micro scale. You're looking at in a neighborhood. You can then move up to what we call a middle scale, neighborhood scale. So now we're looking at a kilometer level. We can look at it at an urban scale. So for instance, we look at it for the city of Lansing. And we only have 1 or 2 monitoring stations for the city of Lansing. So we're really looking at that at an urban scale. Regional scale, we're looking at, for instance, the East Coast. So maybe we're looking at the Northeast Corridor. So between Washington, D.C. and Boston. And we're looking at the air quality in that region here. So we're going to set up our monitoring stations differently depending on the scale at which we wish to identify the issue. So for example, quite a few years ago, I worked on a site remediation near Akron, Ohio, and it was an old metal plating facility, very high levels of metals in the soil. And one of the concerns was the particulate levels in the air during the excavation and any particulate levels in the neighborhood from the trucks as they left the site. So in that case, we really were looking at a micro scale. We had monitoring stations set up at the periphery of the site so that we could monitor both particulate levels and also metal levels. It was copper, nickel, chromium. We needed to measure those on the particulates to ensure that the population in the surrounding area were not exposed to these toxic metals. And then what we did actually for them in the community was they actually had a washing station, and the truck tires were washed down to try and reduce the amount of particulates. And then we had several monitoring stations in the neighborhood, again on the truck route, to ensure that exposures were insignificant. So it's because there we were really looking at kind of this macro scale and just into the neighborhood scale. So when you're looking at selecting the sites, you need to define the purpose of the collected data, as I just mentioned. You need to assemble site selection aids. So when we worked with the consulting firm and the client on this site, we looked at climatological data. What was the prevailing wind direction? Topography was pretty insignificant on this site. It was a relatively small site. It was flat. We looked at the population. Where was the population located? And how could we ensure that the population were not exposed? That helped to determine the sampling locations. If you're looking at an industrial source, then you're going to look at the emission inventory data. So for instance, if you wanted to know what the SO2 levels were from the MSU power plant or the NOx levels from the MSU power plant, you could obtain the emission inventory data. They have to sample. There are sampling locations in the stack. They're continuously monitoring. And actually, once a year, they bring in an outside firm to do the QA, to check all of the devices, to ensure that the values that they're getting are accurate and precise. You may also want to do some diffusion modeling to determine what, again, looking at prevailing wind direction. Where are people most likely to be exposed, or what environmental areas are most likely to be exposed? And that helps define where you locate the samplers, what type of samplers, what you're measuring, how often you're measuring, etc. So that sets up the network. Just to give you an idea of the Michigan Air Monitoring Network, these are the monitoring stations, so you can see where they're located. The Lansing-Feely Street location was the one that I used for much of the data in the air quality presentation that I recorded and posted online. So you'll see that most of that data is available. I've given you links for additional data. You can also look for your report at any of the sites. If you're looking at Michigan, any of these sites. And you can see there's a concentration of sites in Wayne County. It's concentration of population in Wayne County. Not all sites measure all analytes. So for instance, these are the sites that measure PM 2.5. And if we go back here, there's a few like Beckling, Evans, that are on this one. They may be measuring ozone, but they're not necessarily, this case, they're not measuring PM 2.5. These are the only sites that measure PM 2.5. Then we also have mobile monitoring and surveillance, and this is typically used for studying atmospheric transport, chemical transformation processes, and also transient sources. So for example, the meltdown of the Fukushima nuclear power plant, there was extensive air sampling done for radiation. This was all done by planes. So they flew planes into kind of across the Pacific, and they were continuously monitoring for radiation from the Fukushima nuclear power plant. Same thing can be done with fires. So you can monitor particulate matters. Volcanoes, similar event. So you can use these mobile stations for these types of transient sources. The advantage is you're getting instantaneous information for an event as it's occurring. So you isn't necessarily stationary fixed monitors set up, so you need to get this information at the location. The challenge is there aren't a lot of planes equipped with this instrumentation. It has to operate on a mobile platform. Temperature, pressure differences can cause problems. Size, power, weight of the instrumentation can also cause problems. So it's not a trivial effort to do, but it actually is a very, very powerful tool when we need it. Overall, the goal of, as I mentioned, going back to the beginning, we want samples that are representative of the air that we're breathing or that is emitting from the stack. So we need to make sure that we have a proper quality assurance, quality control. This is all stipulated by EPA. There are books and books on this. There are regulations on this. This is how often they have to do the checks, how often they have to calibrate, what sort of control charts they need, when corrective actions that are necessary, preventive maintenance that is required, along with the record keeping and the documentation of all activities. Power plant, they have to do all of this. They have to sample, they have to calibrate, they have to have the control charts. All of this has to be maintained. It also has to be maintained for each and every one of those sampling locations that you saw in the map on the previous slide. So hopefully this gives you a sense of the different principles involved in ambient air monitoring, in stack monitoring, and have a better appreciation for what is done to protect human health and the environment.